Morning class, and today we're going to go over the third example on our multiple step problem worksheet. This one's definitely a bit of a doozy. Let's jump in. A 5 kilogram box is sitting on a table with a coefficient of friction of 0.22. A 0.30 kilogram sticky ball is thrown at a box with a velocity of 12 meters per second. When the ball hits the box, they stick together, and how far will the box slide on the table after the collision? Whew, a lot going on in this one. But if I was to try to think about this and then summarize it, I'm throwing a ball at a box and they collide, and then the ball slides across the table. All right, we have our and then set up, but this one is definitely a tricky one. I'm going to color code highlight my information again. So yellow will be before the and then, and green will be after the and then. That 5 kilograms exists at all times. Your coefficient of friction is all about when friction is happening. And friction is only happening when something is moving across a surface. In other words, the box sliding across the table. So your coefficient of friction is something that we'll use in the after the and then. The mass of this sticky ball doesn't change, so it's usable on both sides. And it's thrown at the box at a velocity of 12 meters per second. This is before it collides, so this is in our yellow section. When the ball hits the box, they stick together. That's going to be a hint that we're going to use later. And then we're asking, how far will the box slide is the question, and that question is going to be in our green section. Now, when we ask ourselves how far will the box slide, we're asking ourselves a displacement question. We have only been finding displacements when we're using kinematics. So I'm going to immediately begin by trying to list my kinematic variables to help me. What things do we know? Well, I know the box is sliding across the table and there's friction, so it's slowing down. And if I ask how far it slides, I want to know how far will it go until it stops sliding. And how far will it go when it stops sliding? Well, that implies that our final velocity is 0 meters per second. However, we have no information about the initial velocity, nor do we have any information about the acceleration, nor do we have any information about the time. Well, what sort of things can we figure out? There's a key word that's been telling me to do something. The word collide has been telling me that I should be using the law of conservation of momentum. So if I considered using the law of conservation of momentum, how would that help me? Let's take a moment to check. Before, I had a ball and a box, and the ball was moving. And after, I have a ball stuck to a box, and they're both moving. Ah, you might see that the final velocity in this case is going to be the velocity that it begins sliding across the table. So I'm going to use my law of conservation of momentum to do this. I'm going to call my ball B, and I'm going to call my box C, because I'm going to call it a crate. That way I can use different variables. So mass of ball multiplied by the initial velocity of the ball plus the mass of the crate multiplied by the initial velocity of the crate. That's my total initial momentum. And it looks like I have one object, right? It's the ball and the crate stuck together, and I'd be able to find that one velocity that they have. Let's plug in the variables and see what we have. And we see that the VF in our law of conservation of momentum is 0.679, but that's the velocity that the box begins sliding across the table, 0.679 meters per second. Excellent. That's one piece of information solved, and that's going to be very helpful. But unfortunately, we still don't have enough information yet. If only there was some other thing for us to be able to solve. Well, maybe I could find either acceleration or time. One thing that we haven't talked about is our friction. Friction is a force, and I know forces can help find my acceleration. So I'm not going to find time, I'm going to find my acceleration. And let's begin this by making a free body diagram to help us know what's going on. Here's our box with a ball stuck to it sliding across the ground. There's going to be a little bit of gravity pulling it down. There's going to be some normal force keeping it from breaking through the table. And while it's sliding forward, there's going to be friction trying to pull it down, pull it back. Analyzing this, our net force is only the friction. So if I can find the value for my friction, I'll be able to solve for this very well. And you know what? We can find for our value for the friction because it's just going to be the coefficient of friction, which we're given in the problem, multiplied by the normal force. And we know that that will equal our mass multiplied by our acceleration because that's our formula for net force. So we're going to take our calculators and calculate our force of gravity because we also know our normal force is balancing our force of gravity. 51.94 newtons, which means our normal force is 51.94 newtons. The mass of this object is 5.3 multiplied by our acceleration is equal to our coefficient of friction, 0.22, multiplied by our normal force, 51.94. Now let's do this calculator work. And we see the acceleration is 2.156 meters per second squared. One thing to note here is that the force of friction is in the opposite direction of the motion. So I'm going to give it a negative sign. And I can substitute this in here. Negative 2.156 meters per second squared. Now I have three known variables. That is enough for me to solve using kinematics. I'm going to use all this information now to get my final solution. I'm going to use the formula Vf squared is equal to Vi squared plus 2 times A times D. The displacement is 0.11 meters, or you can say that it slid 11 centimeters before friction made it come to a stop. This type of problem is the ultimate problem that we're looking at here in physics. As you can see, it makes us use everything we've learned so far. We've had to use kinematics, we've had to use forces, and we had to use momentum to try to put all of our pieces together. This is the thing that we're trying to build to, being able to solve problems like this by putting all of our ideas together. We're going to be practicing this more in the next week, and then we're going to wrap up our semester by looking at a little bit of energy. Have a good day.